Okay, so let's continue, please. So from the previous hand session, we finished with this, right? So we already created this postcard. So look this, I'm going to, so everyone should have this file. So I'm going to minus B, this one, right? So everyone has this structure so far, right? This is the structure that we need to manipulate, right? So just to get this structure, remember that we did is first of all, we relax only the hydrogens, and after that, we create this, after relaxation of the hydrogens, what we did is we generate this structure, and now we manipulate this, this, we manipulate this in such a way that after we fix all these, this hydrogen and the silicon. So that's it, right? So this is after doing a quick relaxation on the hydrogens. And now what we're going to do is, since the reconstruction is, it is suggested to be 2 by 2, we're going to check this, please. What we're going to do is now is to expand this 2 times in X and Y direction. So we're going to create a new superset to get this, what is mentioned in the manual. So please, everyone, open with ASE the file called Oscar 1 by 1 L5 E10 hyperpinic because we did the last, that's the structure of the last session, remember this? So everyone has, right? So now, if you once you have this, you have this structure, so we are going to expand this, you see, in the 2 times in X, 2 times in Y. Okay, so let's put this with tools. We come here, I think it's in view. In view, you go to repeat, and you are going to put 2 by 2. Okay. Once you have this 2 by 2, you are going to put set unit cell. Okay. And after that, let's see, if you press the keyboard equal, you're going to have this. Okay. So this is the structure 2 by 2. Okay. So this is the structure we are going to investigate now to get the surface structure, right? So this is the 2 by 2. Okay. So now it says in the manual says, so we're going to create this and we're going to save it as this, okay? As postcard hyphen 2 by 2, el 5 y 10 have init dot postcard, right? So we're going to save this like this. So let's save it like this, please. So, but anyways, somebody will need me to repeat this, what I did is to get this structure, please. Anyone, please? Somebody need my help, please? No? Is that okay? So this is the structure we have. So it's 2 by 2. If you want, I can repeat this again. So I'm going to pause this. So after this, you, as I mentioned this, I repeat again, you failed, save this file as a postcard, you see. Postcard iPhone 2 by 2 L5. And you see it. And you press enter and you will save this structure, okay? So I will say, because I already have this file, it's okay. So I'm good because I already have this file. So I saved it already. So just in case, I'm going to close this. And I'm going to check this file, right? So let me see if it is this file 2 by 2 L5. Let me see 2 by 2 L5 is this, you see? So please check this, check this, this computer. Okay, this is the structure. Okay. We have to fix this because we want to put first of all the silicons and after the hydrogen. But we have to fix this before and look at what is the structure we have. There it is. Okay. So everyone take care, please. I'm going to pause the recording. So this is the structure. Look this. This is the order of the atoms. In our case, we need to put first of all the silicon, all the silicons, and after the hydrogen. But okay, so we are going to do this in a moment. But before, as you can see here, you see, we need to edit that file and sort the silicon and first and after the hydrogen coordinates, right? Uh, Now we can do this, right? So we are going to fix this, please. So let's do this. Where is this? The structure there. So where is the postcard 2 by 2? This one. So please, what we have to do is to fix this, the order of the of the structure, right? So we have how we can proceed. First of all, the first silicons, the first 5 atoms are silicon. 1, 2, 3, 4, 5. You see? Next are the hydrogens. So this is the hydrogens. Next are 5 silicons. 1, 2, 3, 5. Next are hydrogens, as you can see here. I just separate the hydrogen, these silicons. Next are hydrogens, are silicons. Next hydrogens. And finally, this is the. So what I do is, you see, I take these 2 hydrogens and I paste it below the last one because these 2 are hydrogens. Please come in. Okay, so I erase this. See, these hydrogens, I have to copy this, paste it here, right? And finally, these 2 last hydrogens here. So in total, it has to be, okay, so there has to be 1, 2, 3. So this is the distribution of silicons and here hydrogens, okay? So there has to be, how many sil how many silicons, please? 1 second. Okay, so there has to be 5. Look this, how many silicons there has to be, so we can open this and this, but anyways, has to be more or less 5, 10, 15, 20 silicons and 10 hydrogens, as you can see. There has to be 10 hydrogens. 2, 2, 4, 6, 8, 8 hydrogens. 8 hydrogens. 1, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, as you can see. 8 hydrogens, and there has to be 5, 10, 15, 20 silicon atoms. Okay, so in that case, I fix it like this, as you can see. Breathe. So we fix it like this, and after that, there it is. That is the structure. You see, so I put 20 silicons and 8 hydrogens, and that's it. So this is the way that we fixed this, and this is this. Okay, I'm going to pause this here. This is the. I'm going to show you other way to do the same, please. Okay, so you can do by hand or you can do like this, for instance. Right? You open. First of all, I'm going to replicate again this how I did for the students that arrive. I'm going to replicate what I did, please. Okay. I'm going to repeat another way this because it is already recorded the previous, so you can check this. But for instance, this, right? So I want to, first of all, I have to do a 2 by 2 supercell. So I press R, I press this 2 by 2. You check this. Still is not a supercell. So here you have to create set unit cell, you see? Look the arrows here, the square. This is the unit cell, as you can see. If you press here set unit cell, look what happened with the dashed lines here. You see? See now the dashed lines here. So it means that this is the new supercell. Okay. Second thing. Okay. Now we save this, as I mentioned before. Save, right? As a postcard 2 by 2. Postcard. What's the name? as a postcard 2x2 hyphen like this. Okay, so I'm going to save it like this. Okay, okay, I save it. Since I have already saved it like that I am overwriting, it's fine. But now you see, I keep open this, and then this is the other way to do it, by the way. So I erase all the hydrogens. You see, 8 hydrogens I erase, delete. Okay, and I'm going to save this file, save as I'm going to put only, let's say, silicon. This is atoms. See, I'm going to save it like this. Okay, silicon atoms. Okay, I close this again, please. You see, and I'm going to reopen the postcard, the one that we created. Okay, the postcard 2x2. And in this case, I'm going to erase all the silicons except the hydrogen atoms. The 20 silicons, you see here, 20 silicons. Okay, and I'm going to, there has to be 8 hydrogens, by the way. Yes, 8 hydrogen. I'm going to save it as a hydrogen atoms. See? Okay. So this is other way to do it. So I'm going to close this. All right. Okay. And now you can open this, the silicon. What is this file? Silicon I created. Silicon. What is the silicon atom? What is this? No, I hope, I suppose I create this. No, there is no here. Okay, so I'm have to, I was thinking I was creating this. Let me see. No, so I will repeat this again anyways. Okay, so I open again this, look this, I press 1, and I erase all the hydrogen atoms. Please let's erase first all the hydrogen. Delete. And now import this as a silicon con atoms. So better is to put just dot postcard, maybe to make it clear what I want. Let me see if it's what it was created. There it is, silicon atoms dot postcard. And now I'm going to close this and open this again, this file. And now in this case, I'm going to select all the silicon atoms and save it. This is only hydrogen atoms, right? File, save it as a hydrogen atoms dot postcard. See? And I have this. Let me see. Hydrogen atoms here. Okay. So there it is. Close this, please. And now what we have to do is to put together, right? So if I open, let's open the postcard 2x2. This, look how it is. Is in the arrangement I don't like, right? So I have to reorder this. So one way to do it is as we did before. Other way to do it is just select everything here. I'm going to erase this. And I'm going to paste here the postcard file of the silicon atoms, right? So these are silicon atoms. As you can see, there are 20 silicon atoms. So I'm going to copy this, paste it here. And now next, I'm going to paste it the hydrogen atoms. So what is the hydrogen atoms? Here it is. See? The 8 hydrogen atoms. And that's it. So this is the other way to do it the same. And both of them are, is correct. So there are 20 hydrogen silicon atoms and 8 hydrogen atoms. And that's it. So that will be the way how to build this. Okay. Once you create the file, please do not you do not be, overconfident that it's fine. Always you have to open this file. Okay, so if I did this correct, let me see if I open up this in ACE and let's see it's correct. I'm going to open in ACE, and let's see ACE. Why not be? So I have it here. Okay, so now this file is the new one that is edited, and it has to look something as I was expecting, right? Okay, so there it is. Okay. If you can open an asset, knowing that you arrange the hydrogen and the silicon, you have to have something safe. So that is as expected, right? As you see, graphically it looks there is no changes, but the point is how you order the atoms in the Postcard file is very important for our program to understand what is the silicon atom, what is hydrogen atoms, and okay, right? If you fail that, even though the Postcard file could look fine, if you do the calculation, then you mix the order. You see, you put first of all hydrogen and silicon, or in your Postcard file, you put first of all the hydrogen and after silicon. This would be a totally crazy calculation, right? So maybe will explode, okay? And it's going to explode because in past we think that the silicon atoms are hydrogen and the hydrogen are silicon. And it will be completely a total mess, right? And that is normal, sometimes that is a normal mistake that when you start to do this type of calculation. So it's strongly recommended that before you do the calculations, remember what is the order in your Postcard file you put first silicon and then the hydrogens. In my Postcard file, the first atoms has to be silicon and the last atom has to be hydrogens. By the way, you can check even the indexing, right? So if you're not sure, you know that the number, the zero atom or one atom has to be silicon. So you can come here and you can in view, you can say here levels and you can check this atom index. You see in view, levels, atom index, and you can see the number of the atoms. Remember this assay name the atoms starting from 0. So 0 is the first value of my atoms in my Postcard file. So this is for me the first atom, right? Just in case. Or you want to relate the number of atoms, you just add +1, so it will be 1, 3, this will be 2 or so. And as you can see, this is all this, 26, 27, you see, all that are involved in this thing. So everything. Okay. Questions here, please, somebody? Questions, please. Okay, so right now we have the initial structure that we are going to use to find out what will be the actual surfaces reconstruction of this material. For this, we're going to mix two things, the machine learning and ab initio calculation, right? So in the old days when we were not having this machine learning, the calculations are very long, it can take a couple of hours to get the structure we need. So, but right now we're going to speed up the process of these calculations using machine learning. So in the first step, if you read the manual, is that we are going to use the previous generating, we generate machine learning force field on the bulk structure. So we're going to apply this machine learning, this is not correct way, but anyways, we have at least some model of machine learning from the machine learning to take into account the interaction between silicon atoms, but only with silicon atoms. So we don't have information of the hydrogen atoms. Therefore, we're going to do the first step, at least just to speed up, as I mentioned this. We're going to raise all the hydrogens and we're going to leave only the silicon atoms, as you can see here in this image. And plus, we're going to break the symmetry of the structure with this, That is very, 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 is not, it's a little bit intuitive why I'm doing this, because remember these hydrogen atoms, these silicon atoms here, I'm going to show you here. As you can see, these silicon atoms here has two dangling bonds, right? You see? These atoms here in the surface has each one has two dangling bonds. Therefore, it should be more stable if at least we allow them to form some bonding into this. And the only way to do this is just to move these atoms here, these atoms in this part here, one against each other. So I'm going to take this atom here. I'm going to take this atom here and to move it to the left, and this atom here to move it to the right, right? So this protein will move to the right, this to the left, and also on the below that, right? So on the back of this, right? You see these atoms. So I repeat again what I'm going to do here. Why I'm doing this? Because this is the only way that I can allow these silicon atoms to create a some sort of bond, right? Because remember, two dangling bonds are very reactive. It's not this should be not stable. It's, let's say, not stable, right? So since we want to check what is the structure of the pristine silicon surface, so I cannot put here atoms to passivate, right? So that's the reason why we have to try to allow the system to get the most stable structure. And the most stable structure normally is related with the bonding, right? So we at least we have to create some bonding between of these silicon atoms to give some bonding to the silicon atom. The only way to do it is just to put this two. So please, so this is the way that we're going to do, right? So in, as I mentioned, the previous days before machine learning, there was no way to get, I mean, to give this calculation because there was no machine learning, and therefore we have to do many calculations on the surface to find out what is the most stable. So let's use this, okay? So as mentioned in the manual, please, we're going to please open the structure postcard. Okay, I'm going to open the structure postcard iPhone 2x2. Okay, let's open this structure, and now we're going to edit this, right? So we're going to edit this structure. Please, I'm going to erase the hydrogen atoms. Select, delete atoms. Okay. Even though we are going to do relaxation on this new structure with the machine learning, and you see here, there is no hydrogens anymore, but I fixed these two silicon atoms, okay? It's not a perfect way because, you know, these atoms are, these dangling bonds might affect the relaxation, but doesn't matter because we are going to pre-relax the structure. And here says the manual, you see, we are going to construct this. We are going to put these silicon atoms close together. So we are going to move, 6 times towards each other in the y-axis, forming what we call symmetrical dimers. So how to do this, please? You select this, please. Look this. With the mouse, with the left hand of your mouse, you do this, right? You see, now there is a dark green halo around the atom. And after that, in tools, you put move selected atoms. You see, and now bright yellow halo will appear, and you press 6 times the left arrow here. So if you see, I'm going to show you what I'm going to do in my keyboard. See, this is my English keyboard, please. And I'm going to press 6 times this keyboard, 6 times, right? These arrows here on my keyboard, right? 1, 2, 1, 2, 3, 4, 5, 6 times. Okay. And I'm going to do the same for the next. So, okay, so I'm going to close this. And now I'm going to do the same for these two atoms that are here. There are two atoms here, this. I select this. Now tools, move selected atoms, right? You see, when you put move selected atom is unselected this, and now still not selecting this. You have two tools here, move selected atoms. Now it's a green arrow, and you press 6 times. 1, 2, 3, 4, 5, 6. And automatically will appear this, this, and that's it. Okay. With this, and I'm going to pause here till everyone is. So somebody might ask, why I just move 6 to the right, 6 to the left? Okay. The criteria is the length of these bonds that is formed here. See, there are two bonds now here. If you move like this, you see two bonds here, created two bonds. We call this a dimer. And this dimer, the distance between this of the length of these bonds has to be more or less the same as, or even bigger, right? It's okay, but cannot be too small compared with the distance between the atoms in the structure. For instance, the silicon distance is this, right? Look this, is 2.36. And now let's see this. Let's see what is the distance between these two dimers. So let's see. Look, control like this, 2.6. Okay, right? 2.6 versus control 2.3. See? So it's a little bit bigger than this. Okay. So that is the thing is that I want to create this kind of try to tell the system to find a more stable structure. And of course, I allow this distance between this not to be not that small than this. If you put, for instance, one Armstrong will be too short a distance, when you start to do the calculation of the structure might explode. So these two silicons might fly away and you destroy the structure. So that's why you have to be careful. Okay. Questions in here, please? Somebody? No? So if that is okay, please save that the structure. We are going to save that the structure because we want to do this, and we're going to save all the we're going to save in the structure Posca hyphen 2x2 silicon like this. Okay. So I'm going to save it like this, please, as Posca 2x2 silicon. That makes sense, right? So it's only 2x2. So I'm going to file, save as a Posca dot, I think it's dot Posca. Right? We're going to save it like this. Okay. And we save it. Enter. That's it. Let me see if it's created this structure, please. A postcard. It has to be a postcard 2x2. Yeah, there it is. You see? There is only silicon atoms, and there it is. You see? There it is. Okay. I'm going to pause here. Okay, so if that structure is fine, please always you have to open this new structure with ACID to check if ACID can open it and inspect that everything looks fine to you, right? So look this. This is a structure I created. There is no hydrogens, plus there is a deformation of the silicon atoms at the surface that forming that bond. And that's it. It looks fine to me. Okay, this is the structure. Okay. Anyone please want me to okay, I'm going to stop, wait a minute here. Okay, I'm going to use this in this section, no? We say check the K-point read. Let me see the postcard file that we want to do this. We have to, first of all, I'm going to set up my, what is named this one, right? So I need this. Right? So I set up my work directory, and after that, I'm going to use this. The check K-point read. Okay, so now I'm going to import the postcard file here. So I'm going to, maybe I can copy this. You can copy this, please. This, and this. Please copy this, please, and paste it here. See? So now I have to import this postcard file that is here. That is in Parsec surf iPhone postcard. Where is this postcard? iPhone 2x2. Select any of these, right? This or this, but I'm going to use this anyways. Okay. And now I'm going to shift enter this. This is the structure. Now the lattice constant like this. And now delta K. What is delta K? I need to generate delta K, please. Delta K is this. This. Delta K is this. And now I'm going to generate this. Okay. So I need I need delta K of 0.075. 0.075. You see, so in this case, my K points has to have a grid of 2 by 2 by 1. Okay. I'm going to pause this here. So once we have this, we have checked the grid we have to use is 2 to 1. So we have to create, or we have to have this file K points -ml 2 by 2. Okay. So this K points has to have the grid 2 by 2 by 1. Okay. And we're going to run this rxo-ml.sh. So let's check that file, please. So what is this? What is this xml rxo? This one. Rxo, what is this? Rxo this one. We're going to run this, please. They call this RXO-ML. RXO because it's a or what is the name? Initial relaxation. It's only to have some good guess before we do a proper calculations. In my case, I'm going to put please only 2 cores. You don't have to do this, please, but I'm going to do this. And you see this is going to enter to the folder called Suruf. Is going to create a link, symbolic link of your force field that we created for the bulk, as you can see here. So we have so we are going to remove the podcast file. We're going to have this, and after this, right? So we are going to have this. You see, we're going to do 2x2 silicon. We have to have this, by the way, 2x2. So in this case, please, since we have to have a file postcard-2x2 silicon, so either you erase this, what is the surf? This postcard. See, this, it has to be just name it a postcard-2x2 silicon, so you can erase this. Either you can do this, right? Or you can change it here in the script. You can put like this dot, whatever you want, but whatever is fine to you. I repeat again. Either you edit this script to put dot postcard, or you put here and you erase what it was before. See, it was original was like this. What I did is just erase this extension dot postcard and like this. So I leave it like this for instance. Okay. So this is fine. So if you leave it like this, you don't have to change anything here. Okay. Now we have to check what is the INCAR MLRX. And after we put this parallelization and the K points, right? So we have to have the K points. Maybe we have to create it, or we have to see if we have this file. CP this K points ML. Probably I have it here in this K points ML. So here it is. Let's see. K points ML 2x2. You see, we already created this. I mean, I put already this file, K points ML 2x2. And as you can see, it has the grid 2, 2, 1. Okay. What else? Since we removed the podcast file, we have to have a podcast file. In this case, we have only a podcast file that depends on the silicon. Why? Because my structure has only silicon atoms. That's the reason the podcast has only the silicon atoms. After we run, we have to have this Concar hyphen 2x2 silicon.rxo, and that's it. Okay, so everything looks fine to me. Okay, I'm going to pause here again. No, and before that, let's check this. What is the INCAR LMLA MLRX? INCAR MLA RX, this one. Look, in this, we have this information, you see. There is no information about the electronic structure. See, this is no ab initio. It's only information about the machine learning and so on, you see. So there it is. So we are going to relax the ions, the forces, and we switch off the symmetry and this machine learning. So this means that we are going to use the already computed machine learning to do the calculations, right? INCAR MLA. This one. See this, that's it. Okay. So there it is, and that's it. So we have everything. Okay, I'm going to pause here. Before you run, check that in your script, you're asking for the existence of this file, postcard hyphen 2x2 silicon. Let me see if there is this file, postcard hyphen 2x2 silicon. There is, yes, this file, right? I repeat again, when I create this, it was postcard hyphen 2x2 silicon dot postcard. So what I did is I just removed this. And now I'm ready to run, right? I have to run this, somebody's running, right? RXO. Sorry. Okay, so you have to go back to this to find the script. This is the script we have to run. This one. All right, so this one, okay? That's it. Finished. Okay. So this has to be the source. And it has to be the concar, you see, 2x2, this one. Was created this. See? I'm going to pause here. Let me see. AC minus B. I'm going to check this file, please. There it is. This is the relaxed structure that I created, right? And also, I'm going to close this. We have to, it was, let me see the output, right? This output, iPhone. Oh, let me open this way. The output, where is the output? iPhone 2x2, this one. There is this, you see? It takes, in my case, takes less than a second to do the whole relaxation. This is the relaxation. It did, in my case, it did 19 relaxations and reached the accuracy stop energy minimization. Okay, so just in case, if you check the distance between the two, the concar file, the two silicon atoms, you are going to see, in my case, I have 2.321. In your cases, maybe we are going to have a dispersion of results based on your force field that you created. This force field, of course, depends on how many force you use and so on, you know. But the point is that this is just initial step. At the end, but to compute the final actual structure, we have to do some last initial calculation to get the results that we want to get and to compute the electronic average surface, to compute the steam images and to compare the experiments. Okay. So in this case, what we did is only to speed up to have some initial guess of the structure, because now we have to put the hydrogens to train again the machine learning, and after that we do again the next verification only with the machine learning. In fact, what we're going to do is we're going to rise the temperature to 400 Kelvin to leave it from somewhere there, and after to drop this to 0 Kelvin, and after that we are going to get the actual structure, do the final initial relaxation, and that's it. That will be the process. Okay. Okay. So let's continue, please. Any question here, please? Did you check the distance between the silicon atoms, please? You can check this. In my case, as I mentioned here, it is this, right? So I'm going to open this. Control. What is important from here is, with this even allow me to check that if my starting guess was good enough. If you put the value too close, you're going to see the machine learning will explode. Your structure will might explode, right? So it's better to check this, that if you did something wrong about this initial guess with machine learning rather than doing ab initio. Ab initio will take hours, and after you find out the structure will explode, and you lost hours of calculations. In this case, in less than a second, you can find out this your initial guess is reasonable. That's the point. That is the thing that we want to get from. Okay. Question here, please. Somebody? No questions? Questions? Okay. So I'm going to go to the next part. So please, I'm going to close this. I'm going to close this. In my case, by the way, it takes 19 iterations here. So now we are going to start to create the input file for what will be the final training of the machine learning for computing the surface structure. Why we do this step? Because we have to include also the information of the hydrogen. That is the reason we have to train my machine learning. But for that, we are going to start from the relaxed structure of only the silicons and included the hydrogen atoms. For that, first of all, open the concar file, this concar file by 2. Okay. Open this. And please save it as let's save it as a silicon. Okay, file. Save it as a silicon hyphen by 2 dot Postgre. Okay, I will explain why. Okay, we're going to open this Concar 2 by 2 silicon disk, and you're going to save it as a silicon 2 by 2 Postgre. Why? I will explain why. Okay, so please do this. Save it as this name, please. Silicon 2 by 2. Silicon hyphen 2 by 2 dot Postgre. Okay, when you do this, look what happened. First of all, look at the Concar file. Okay, look this. It says this structure is given in when they said direct or fractional coordinates. So the coordinates of these silicon atoms are given in fractional coordinates. Since we want to edit this Postgre hyphen init, right? This one, Postgre hyphen init, this one. We want to edit this. We want to replace the silicon with this. Look, we cannot do it directly. Why? Because here we have Cartesian coordinates and we have here fractional coordinates. So here I have to give these coordinates in Cartesian coordinates. And for that reason, when you do this step of the saving as a silicon, this 2 by 2, this one, please, you get as a Cartesian coordinates. Now it's safe. You can copy this, right? Right? And paste this, okay? So we're going to paste here, and we're going to save this as a, you see this one? Here. So 8, 1, 2, 3, 4, 5, 6, 7, 8. So till here, please. These 8 are untouched because there are hydrogens and here. Okay? And save it. And save it. Or you save it as this. This is one way. Other way is doing this. You see? This is the other way to do this. Other way to do exactly the same, and is this. Open this Concar file, right? This. This is the one that will relax, and save it. Please save it, file, save it as it says the manual, Postgre hyphen bitten new dot Postgre, like this. Postgre hyphen 2 by 2 L5 B10 hyphen in. So this is my second way to do it. I think it's okay. So we have already the postcard this, but I need to include the information of the hydrogen atoms. Okay, so I'm going to close this and open this postcard hyphen, what is this? Init. Yes, new. This one, you see? This atom, has the structure of only the information about the silicon atoms. What I have to include here at the bottom is the information of the hydrogen atoms. What hydrogen atoms? And here, that is here. You look at this and you just copy this hydrogen atoms here. There has to be 8 hydrogen atoms. You see 1, 2, 3, 4, 5, 6, 7, 8. And you paste it in this new one. This is init new. Save it. And don't forget to put this silicon and hydrogen 8. And this silicon and there it is. Okay. I'm going to repeat it. Okay, I'm going to pause this here. Please check the Postgre file hyphen 2 by 2 L5B10 in a new Postgre. You have to have exactly the same hydrogens, roughly the same hydrogen coordinates when you paste it here. And these are the coordinates of the silicon atoms were fixed. Basically, you have to have basically the same or almost the same values here. These are the hydrogens that were fixed during the calculations on with my force field. And finally, the other coordinates could be a little bit different, but doesn't matter because we want to start to train your machine learning based on this. Okay. Okay, so we have this. We have already this. The key points we have to use we are going to use to train again the machine learning is going to be the same. So we are going to go, you see, to do the complete the training of machine learning, we want to use, or we are going to use this file. This file ml-abn has all the information about what it was computed before in machine learning, like position of the atoms, you know, the forces, the energies, and the stress. It has all the information that we did on the previous machine learning training on the force field. Right now, we are going to use this to keep training to include the hydrogen atoms and also the silicon atoms that are in the surface, these dimers that we just saw this, right? So we are going to use this ml.sh. Where is this? ml.sh is here, please. We're going to use this script, please. Okay. Look this. I just put here. You can skip this. I mean, I put course 4, but please, in your case, you have to have something like this, right? See? Okay. So I have this. Okay. This is that's it. Mhm. So it's going to call the incar ML, So you see it here. So we're going to call the incar ML, as you can see here. And in this case, we have to check the key points and so on. Okay, so 1 second, please. I have to check this.